Hey guys, it's Megan. I'm going to be talking to you about global warming and its effects on Florida's ecotone, the transition zone between the coastal mangroves and the cypress swamp. When most people think of the swamps of South Florida, they think Everglades. However, the immense wilderness of marshes, bogs, hammocks, and the river of grass between Naples and Miami are actually two ecosystems, the Everglades and Big Cypress. Big Cypress and the Everglades are separate geographic features with slightly different topographies, with Big Cypress being 1 or 2 feet higher in elevation. A peninsular divide with water flowing in different directions on either side separates the two ecosystems. The broad savannas of the Everglades give way to the uplands and tree hammocks in the Big Cypress. The most significant difference between the two ecosystems is that the Everglades is ill. Farms and chemical runoff, diversion of water from Lake Okeechobee, and encroaching development from the East Coast has reduced the Everglades to approximately one-half its original size. On the other hand, Big Cypress is healthy and much larger than the Everglades, with over 2,400 square miles of subtropical acreage. Florida is home to approximately 469,000 acres of this dominant subtropical coastal ecosystem. Florida's mangrove swamps are concentrated along the southwest coast, where the Everglades and Big Cypress Swamp drain into the Gulf of Mexico. Mangroves are one of Florida's true natives. They thrive in salty environments because they can obtain fresh water from salt water. Some secrete excess salt through their leaves, while others block absorption of salt at the roots. This ecosystem traps and cycles various organic materials, chemical elements, and important nutrients. Mangrove roots act not only as a physical trap, but provide attachment services for various marine organisms. Many of these attached organisms filter water through their bodies and, in turn, trap and cycle nutrients. 3 of the 10 known mangrove species dominate Florida's mangroves: red mangroves, black mangroves, and white mangroves. Florida's mangroves are a tropical species. Therefore, they are sensitive to extreme temperature fluctuations as well as sub-freezing temperatures. The name Big Cypress defines the size of the area, not the size of the trees. Most species in the Big Cypress are dwarf pond cypress variety, mere shadows of the once large cypress trees in the preserve that were logged out between 1920 and 1950. Today, the Big Cypress National Preserve consists of 728,000 acres located in the Collier and Lee counties, in the southwest of Florida. The Big Cypress has no outside source of water. Over 97% of the water is supplied by rain, with 60 inches of rainfall in an average year. Cypress trees grow in water that are found growing in solution holes. Solution holes are depressions in the limestone bedrock that have been broken down over time as a result of anaerobic decomposition of leaves, branches, and flowers. This process creates a byproduct that is acidic and over time dissolves the limestone bedrock. The roots of the cypress trees are able to break through the bedrock and take hold to grow. Among various factors driving the distribution of mangroves and marshes, sea level rise has been reported to be the primary driver of mangrove encroachment in South Florida. More importantly, if sea level rise continues at the current rate of 2.33 millimeters per year in South Florida, the majority of coastal ecosystems in the Everglades will face profound hydrological and structural changes by the end of the 21st century. In addition to sea level rise, drivers behind the mangrove encroachment in coastal regions of North America include rise in winter air temperature, shortage in freshwater input, and natural disturbances. Field investigations show that various tidal freshwater forests in South Florida, and on a larger scale the Gulf of Mexico, are undergoing dieback reportedly related to saltwater intrusion and surge events. The degree and process of tidal freshwater forest degradation can be subtle, with the initial loss of species diversity, lack of seedling regeneration, and disjunct size class distributions of more salt-sensitive species. As tidal freshwater forests undergo dieback and deterioration, they are succeeded by encroaching emergent marsh. This successional sequence implies that tidal freshwater forest and adjoining upland forests in upper estuary settings are more vulnerable to retreat and loss from sea level rise than any other coastal habitat. The Florida Peninsula has warmed more than 1 degree Fahrenheit during the last century. Higher air temperatures increases the rate at which water evaporates, or transpires, into the air from soils, plants, and surface water. As mentioned before, Florida's mangroves are tropical species. Therefore, they are sensitive to extreme temperature fluctuations as well as subfreezing temperatures. Research indicates that salinity, water temperature, tidal fluctuations, and soil also affect growth and distribution of mangroves. In the coming decades, rising temperatures are likely to increase storm damages and harm coral reefs. Florida, like so many states up and down the Atlantic and Gulf coasts, has witnessed an increase in extreme weather events as a result of our changing climate. The reason why is fairly simple science. For a long time, we've understood, based on some pretty simple physics, that as you warm the ocean surface, you're gonna get more intense hurricanes. Whether you get more hurricanes or fewer hurricanes, the strongest storms will tend to become more stronger. So, as sea surface temperatures become warmer, hurricanes become more powerful. In September of last year, as Hurricane Irma tore through the southern United States, fierce winds battered the Florida's Everglades National Park. NASA scientists recently conducted an aerial survey of the Everglades to assess the impact of the storm, and found massive damage to the region's mangrove forest. As NASA explains on its website, the goal of the 2017 project was to find out how freshwater ecosystems, like the marshes of the Everglades, are transitioning to saltwater ecosystems due to the rising sea level and coastal erosion. By comparing images from this dataset, the information gleaned from the most recent aerial survey, researchers were able to assess how the Everglades changed after Irma. Because irrigated farmland would need more water, the total demand for water is likely to increase more than 25% during the next half-century. But the amount of available water is unlikely to increase significantly. In fact, it may decrease. The Everglades are vulnerable to both changing climate and rising sea level. Human activities have impaired this ecosystem by diverting the natural flow of water away from the Everglades to prevent flooding or to supply farmers and municipalities with water. Coastlines are being developed rapidly and intensely in the United States and worldwide. The population of Central and South Florida, for example, has grown by 6 million since 1990. Many of these cities and towns face the brunt damage from hurricanes. In addition, rapid coastal development is destroying natural ecosystems like marshes, mangroves, oyster reefs, and coral reefs, resources that help protect us from catastrophes. In the 1920s, canals were dug into Cape Sable to drain the freshwater marshes, but instead facilitated saltwater intrusion. By the time aerial photography became widely available in the 1930s and 40s, much of this freshwater marsh had disappeared, converting to open water rather than a mangrove forest. Thanks to years of development, mismanagement, and now epic hurricane, that shock absorber is being pushed to the limit. Sea levels are rising at a rate faster than what many marshes can adapt to on their own. In the future, sea level rise will likely rise even faster. But how fast and by how much demands enormously on the actions we take now. If we continue to emit greenhouse gases like we have in the recent years, the climate will warm rapidly and virtually all Florida salt marshes will be critically endangered. But if we act quickly to reduce our greenhouse gas emissions, protect important land near existing salt marshes, and support salt marsh restoration projects, we can preserve much of what exists today and give the marshes room to grow into.